code walkthrough session, so I was planning to basically go to the IPsec node, which is I would say probably the shortest one we have in the code base. So, and basically explain all the components we have inside the code to basically create the new type of interface, which is a kind of tunnel interface. In this case, it's basically very simple. We have two implementations of IPsec. One is fully RFC compliant with ability to do matching of the traffic and doing drop, protect, or bypass, which is according to the IPsec architecture described in RFC. But also we have a simpler version, which is basically a very simple tunnel, which does encryption. And basically that tunnel is, so we are not matching against any specific access list. We are just sending packets to the tunnel, and all packets are encrypted and sent as IPsec ESP packets to the remote side. So the code you can see is basically in VNet IPsec if out, and we also have IPsec if and IPsec if in. So basically 3 C files. First one is handling the IPsec if is handling basically the initialization and creation of the interfaces. IPsec interface in is the encapsulation node. So basically encrypted traffic coming from remote side, which should be decrypted and sent to the fib, and then whenever it needs to go. And the third one is IPsec interface out file, which basically covers the encapsulation side. So let me start with the IPsec interface.
2 files actually: IPsec input IPv4 and IPsec IF input. And
they're related to the two implementations I mentioned before. So the guys which have IF is a simple tunnel interface, and other files are related to the full RFC compliant IPsec implementation.
So all the IFs is
yes.
Simple tunnel.
So we will focus on those 3 files which have IF in the name. What is shared is header file. So we have the same header file because the security associations are basically same. And what this graph node is doing, we basically IPsec is built in the way that we have 2 graph nodes. First graph node is basically doing the encapsulation and matching the specific security association. So in the case when we are using tunnel, we basically assign the static keys to the IPsec tunnel. But then we have a second node which is called ESP encrypt and ESP decrypt, which is doing the encryption or decryption. So basically the code which I'm going to show is not doing encryption. It's a node before that one, which basically receives the packets which are sent to the interface. It will do a lookup into the interface table, and it will basically find out the matching security association. So basically when after the result of this lookup will be stored to the opaque field in the buffer, which Pierre was talking before. And then when this packet is dispatched to the ESP encrypt node, ESP encrypt node will have all the information it needs to encrypt packets. So basically it will be able to find out what is the security association, what are the crypto keys, and all other information needed to encrypt the packet. So let me start with the main file. So first thing which we need to define is device class. So we are basically creating the new type of the interfaces in VPP, and that device class is called IPsec. And for IPsec interfaces, we are defining the format function and TX trace functions and TX function. Here, actually, this is infrastructure we have for general infrastructure for creating the transmit nodes for physical interfaces. Here we don't need, because we are not transmitting on the physical interface, we don't need to basically create to pass through this TX output node and TX node. So we are basically just creating the dummy interface TX handler, and actually it will never happen that this function is called. So you can see this silly warning. It's basically, if you see this message, something is really wrong in your code. Format IPsec name is very simple format function, which basically generates the interface name. So when you are creating the new interface based on this device class, you are basically saying, when it comes to the creating the interface name, use function which is called format IPsec name. And format IPsec name will basically return string which is IPsec 0, IPsec 1, IPsec 2, and so on. So basically, for every instance of the IPsec tunnel interface, we'll have this device instance number increased, and that will mean that the first interface we create, first tunnel interface we create will be called IPsec 0, second one will be called IPsec 1, and so on. Then we have a main function which is basically creating the interface, and this function is basically called both from CLI and from API. All the parameters we want to send, which are needed to be defined to create the new tunnel interface, are actually inside this structure. So this is basically the structure which contains all the details we need to create the new IPsec tunnel interface. First is add. It's basically flag if we are deleting or adding interface. The second one is extended sequence numbering. Then have a anti-replay flag, IPv4 address for a local side and remote side. We have the local SPI and remote SPI. So this is basically information we are getting from CLI handler or API handler, and they are both calling the same functions by filling this structure. So next thing which is very important is to basically if we have a tunnel encapsulation, we need to have a way how to map receiving traffic to specific tunnel instance we are creating. So we can have like 50, 100, 200 tunnels, and we need to know when we are receiving the incoming packet, encapsulated packet, we need to know what is the key to find the right instance, the right tunnel interface we want to use for decapsulating that packet. So for IPsec case, we are basically using hash, and we are using hash which is called IPsec interface pool index by key. And key is actually U64 value, which is built out of remote IP address and remote SPI. So we are distinguishing tunnels on the VPP side by using those two values as the keys. 32 bits for a remote IP address and 32 bits for SPI. So when we receive packet from remote side, we will use this key to find out our tunnel instance. So first thing we are doing here is basically we are trying to calculate the key, because this is the way to see if there is already same tunnel. We can report error if there is the same tunnel with the same remote IP and remote SPI present in our pool of interfaces. And then if we are adding interface, we are basically first what we are doing. We are first, yeah. So here we in this line we basically calculated the key, unique key for the remote IP address and the remote SPI, and then we are doing hash lookup. And the result of this hash lookup can be something or not. And then if the such key doesn't exist in the hash, then we are safe to create the new interface. If the result of the hash lookup is something, that means that we are duplicating the same interface, and we will basically just return and report error that this interface already exists. So this is basically this check. We are basically coming back from the function saying that this is invalid value. Next, okay, now we know that this is the new tunnel, and we are using the VPP infrastructure pool structure to basically create the new entry in the pool. So basically, pool get aligned will get new slot in the pool of interfaces, of IPsec interfaces, and we are storing this in this variable IM, which is basically IPsec main tunnel interfaces. and T is main per interface structure which we have for IPsec. It's called IPsec tunnel interface T. So this is the structure, which basically contains the security association index, input and output SA index, and also hardware interface index for the tunnel. We don't need a lot of information inside this this structure because all the crypto stuff is already present in the security association database. So we are just saving the pointer to the index of the security association database. Okay, let me go back. Okay, so we basically allocated the new pool of interface structures. Every time we are creating the new tunnel interface, we will create the new entry in this pool. Then, why we are using pool? Because we want to reuse. If we are removing something from the pool, we can reuse that field, and that will basically reduce the number of vector resizes. Because pools are basically what already Pierre was explained this morning. Pools are basically vectors plus bitmaps, and with vector you can just extend it, or you need to shift everything. And with pools you can basically just declare that one field inside the pool is not used, and then when you need the new entry in the pool, you can reuse the same field, so you don't need to resize the memory structure. So here we are using pools, and we have pool for tunnel interfaces, but also we have a pool of security associations, because it can happen that you have multiple security associations which are multiple interfaces which are using the same security association. So basically we are allocating the new security association here, and we are filling the information from the API or from CLI into that security association. So we are creating the new crypto security association. We are setting the source and destination address. We are saying that this structure is tunnel. Use ESN, anti-reply, all the stuff which is crypto stuff we need in IPsec ESP encryption node is now filled into the security association. And now we are doing the same we need to do the same for both directions. So for incoming and outgoing traffic. That's why we are basically creating the two entries in the security association database. First one is this one, this is the second one. And finally, we need to create a hash for this. So next time we have we need to find out from the IP address and the security association and from IP address and from SPI, when we need to find out what is the tunnel interface, we will basically do a hash lookup, and hash set here is basically adding the new hash to the hash table. And parameters are basically IPsec interface pool by index by key, which is the name of the hash, key which we already calculated on the top of this function, and then this last one, this is something which you will see quite a lot in VPP. It's basically index. We are never storing pointers. We are always using indexes when we are storing information. So this is pointer to the first entry in the pool, and this is the element. So basically result of this will be index of the entry in the pool. So first time we call this function, this will be 0, next time it will be 1, 2, 3, and so on. So basically we are adding the hash entry where we are saying for this key, result of the hash lookup will be indexed in the interface database. This part here is basically related on reusing. So when in VPP we are deleting interface by basically disabling them and removing them from the pool. And if we are checking here if we have some free tunnel entries already, so if you create interface, delete interface, and then try to recreate the new interface, we'll basically reuse the existing structures. So basically a result of deletion of the interface is that we are going to add indices to this specific interface to this vector, which is called IPsec main free internal interface indices. So if we have some free ones, we will reuse them. This is this part of the code. If not, we are going to create a new interface. And we are basically calling a function which is called vnet register interface to create the new interface. And the result of this will basically be that you, in show interface, you will see interface called IPsec 0, IPsec 1, and so on. And then finally, we are going to save our hardware interface index to our structure. So basically, it's a kind of helper information we want to store in the structure. Okay. Now, next thing. Okay, so we are creating the first interface. We need to tell to VPP that we are interested to receive ESP traffic, so basically encrypted traffic. And we are doing this exactly with this one, and we need to do this only once, only when first interface is created. We are basically calling a function which is called IP4 register protocol, and we are registering IP IP protocol IPsec ESP, and we are saying that node which should receive packets for this IP protocol is IPsec interface input node. So really, this is the magic which basically attaches this new graph node to the existing VPP.
Does that mean that any IP packet that has IPsec protocol in it will first be given to the IPsec input node here before anything else is done on it?
No, that means that all local packets.
Local packets.
Local packets.
Okay.
So packet will come to so actually the node which will going to send packets to the IPsec interface input nodes is IP4-local.
Okay, so the packet has to hit a local IP
yes,
address.
Yes.
Okay, thank you.
Then we have part which is basically about deleting the interface. We are removing hash from the hash table. We are removing security associations from this SA database. We are basically freeing the pool entry for the interface. Well, I will not go into details. I mean, it's more or less obvious what we are doing here. Okay. I'm trying to see where this function is called from. Anyway, so this is basically how we are creating the new IPsec interface. So every new IPsec interface on VPP is actually the new instance of this structure inside the pool of IPsec interfaces. Now let's go to the input node. So we basically have two graph nodes. One is the graph node which is receiving packets, encrypted packets, and there is another graph node which is sending encrypted packets, right? So it's in and out. This is the in node. And first thing which we are defining here is what are the next nodes for this function. We basically have two of them. We have next ESP decrypt. So basically node which is decrypting encrypted stuff, and then we always use the next drop, which is basically if we find out that some packet is corrupted or there is some other reason to drop it, we are always sending that packet to the error drop node. We are not trying to release buffers by ourselves because it's already done by the error drop node. So it's just easier to just enqueue packet to the error drop node, and error drop node will just drop them and increase counters. Okay, so here we have a function which is basically called format IPsec interface input trace. So when you're doing show trace, the packet tracing, this is actually a function which is going to format the output. And here we have quite a simple format function. It can be quite a big one, but here we are basically just printing in the show trace. We are printing the SPI and sequence number from the ESP packet. So this small structure here is basically the container for sending information from the graph processing node to the format function. You see that we are basically using as an argument, we are using this specific pointer to this specific structure, and then we are just taking values from the structure and printing them on the show trace. And now let me go first down to the definition. This is the definition of what we already saw on the MacSwap example. This is the definition of the IPsec interface input node. We are saying what is the name. We are saying that this is the internal node. We are saying what are the error strings, and actually error strings are mapping to the. You already have infrastructure for counters, and here you are basically saying what possible error counters this graph node can report, and they are defined on the top of this file. We have actually just one counter, which is actually not really error counter, which says RX good packets received. So our graph node is basically increasing this counter for every single encrypted packet received on the node. And on VPP you can do show counters to basically see all the counters which are reported by the graph nodes. That's something I was wondering this morning, because it's something we are just copy pasting, and and I was thinking, why size of utility? I don't know. I need to ask. Okay. So basically, here we are saying what are the error strings for the graph node. We are using error strings or counters. In some places it's error string, and some places counter is basically the same. It can be, if you say in the counter that there is an error, it's error. If you say just receive packets, it's not an error. So it's a bit confusing, but this is how it is today. And finally, here we are statically defining the graph arc nodes, which are our next nodes for this node. And we have two of them. We have a decrypt node, and we have error drop. That's it. Basically, we have so let's go to the main loop. This is the main processing loop for this graph node. It's even not dual looped, so it will be even simpler to follow. We are receiving the frame of frames. We are doing standard get next frame, put next frame, the stuff you saw before on with in the previous session from Ule. Here we are doing calculating the key, the same formula we used before. And then when we receive packet, we are doing hash lookup to find out what is the tunnel instance belonging to this specific packet which is received from the remote side. If there is no result of this lookup, we will just send packet to the drop, because packet is sent to us. It is sent to the local IP address, but we don't have a security association for that packet. So what we can do with him? We are just dropping. So default is drop. But if the result of the hash lookup is something what we have then we will basically do very simple stuff. We are going to fill the opaque area in the vlib buffer metadata to say what is the security association index, and we are setting it to the result of the lookup from the hash. So basically, we receive the ESP packet, we do a lookup, we find the entry in the pool of interfaces of the tunnel interfaces. We found it there. We take data about security association database entry, which contains crypto keys and all the stuff, and then we are basically just putting this to the vlib buffer and dispatching to the decrypt node. Very simple. So we are not doing any magic here in this node. We are just doing the lookups. If there is a result, we will put this to the vlib buffer, and we will dispatch stuff to the ESP decrypt node. If there is no result of the lookup, we will go to default, which is drop. And then another thing which we need to do is to check if somebody enabled trace on the packet. So assuming that most of the packets are not traced, we are predicting that the result of this statement will be false. And we are checking buffer flags. And if there is a flag believe buffer is traced, which is the flag which is set when you do the trace add interface name command. If this flag is enabled, then we will basically add entry to the trace buffer for this specific packet. And that this function will basically call our format function, which is on top of this file, which is actually filling some text into the tracing buffer. So really, the tracing buffer is not much more than a simple string of text, which is multi-line and every graph node is basically just adding his part of the text to that buffer, and that is the purpose of this stuff here. Finally, we have this enqueue stuff, which is already described on the previous session, and we are putting frame to the we are dispatching frame to the next node. And last thing which we are going to do here is increment counter, our famous Eric's good packets counter. So that's it. This is all what we do in this tunnel encapsulation in this input node for IPsec. This is an ESP encrypt node, and this node is quite special. I think it's the only one in the VPP which is doing what I'm going to explain now. It's basically for IPsec we need to encrypt the whole buffer, and it makes sense that instead of encrypting to some temporary buffer and then copying everything back, it makes more sense that we just allocate a new empty buffer, do encryption, and then release the old one. So in this node is actually not sending the old buffer to error drop, but it is just releasing the buffers, and we are doing this in the way that this will be buffer free. At the end of the function, we are basically growing a vector of buffer indices which should be released, and at the end of the function we basically just call will buffer free to free all of them. So actually you can use that trick. Instead of releasing one by one, you can basically give a vector of buffer indices to this function to basically release all of them. So upstairs, so this is the place where we are actually saving the old buffer indices. We have a recycle list inside the processing loop. Every time when we finish with the buffer, we are adding that buffer to the recycle list, and at the end of the function we just release all of them. So you can do this in other nodes, but it's more convenient to just send them to the error drop, because error drop will also take care for counters. On the TX side, we have a similar thing. It's just cheaper because we don't need to do a hash lookup, because we already know when the packet, so basically fib, result of the fib lookup will be the IPsec interface. So we will already know what is our interface index, and based on this we will know what is the tunnel data which we need to do for encrypting packets. So we don't need to use key for a hash lookup. So again, we have a registration for this output node. So it's basically encryption node. Again, we have this time we have a ESP encrypt, so basically node which is doing encryption. And we have again error drop. Same thing like before, errors, counter names, and so on, and main processing loop function. Again, we have a trace because we have trace in both nodes. So this is the trace formatting function for this one. It's basically similar to the previous one. And this is the main loop. Again, it's just a single loop, so it is not, you don't have a double loop here. Dual loop. What we are doing differently in this case, so instead of using the hash lookup, we basically we are basically getting from the buffer, we are getting software IF index of the tunnel interface. This is something which we got from the lookup node. Then we are getting the hardware index of the parent hardware interface index of this software IF index. Inside the hardware interface index, there is something called device instance. It's basically place where the specific interface type is storing the index to the instance of that interface type. And this will basically give us information which tunnel interface this packet should go to. And then we are basically again, we are putting the security association stuff into the opaque data in VLib buffer, and we are dispatching packet to the ESP encrypt node. Again, if we are tracing, we have the block which is doing tracing, enqueue, put next frame, increment encounters, and that's it. So this is a very, very simple sample how to do the full tunnel encapsulation, decapsulation, including all the stuff you need to really on VPP get the special tunnel interface and to have counters and everything. So basically there is no lot of work to create the completely new tunnel encapsulation in VPP. We have some more complex case like GRE where we are basically supporting different encapsulations inside the GRE. So we have subnodes and so on. But this one is really simple, really simple. So it's quite convenient to show how it works. Yeah, so another thing which I would like to show you is a bit about FIB. I don't want to go very deeply into it because there is quite a lot of code. But what is really important for somebody who is developing features on VPP is really to understand how we can use VPP FIB to really do a special treatment for specific destinations, IPv4 or IPv6 destinations. So Ule already mentioned that we are using that for the lightweight for SIP6 map case, where we are basically installing this special FIB entries into the FIB. And with this approach, we are basically telling VPP that instead of sending the packet to the rewrite node and sending stuff out of the VPP, you can basically send the packet which is to the specific graph node inside VPP, the custom graph node. So basically, FIB is hash lookup plus adjacency table. Very simple. The result of the hash lookup is indexed to the adjacency table. When we want to install the new route into VPP, we are basically just creating the new adjacency, and we are adding the route to the hash table. Result of the hash lookup is always something, and that something can be also a drop. So if you take a look into the VNet IP lookup, you can basically see the types of adjacencies which we have in VPP. We have the next miss. We have drop and punt, local, ARP, rewrite, classify. We have map-t, 6RD, indirect lookup, hop-by-hop stuff. So this is what we currently have in VPP as a different results of the lookup different results of the FIB lookup. And the one which is mostly used is actually the guy which is called rewrite. So when you install the new IPv4 or IPv6 route in VPP, it will basically create the new adjacency, which is called rewrite adjacency. And that adjacency will basically point to the graph node, which is called IPv4 rewrite or IPv6 rewrite, depending on the protocol. And that node will basically do a rewrite of the layer 2 header. So when you're installing adjacency to the adjacency table, you're basically also creating the rewrite data. So how this looks like as a structure. So this is basically the FIB adjacency. First thing is that we are trying to align this structure to the cache line, because we want to use one cache line per adjacency. We don't want to have fault sharing in the adjacency. So we are building the adjacency. Actually, what we are using is two cache lines for adjacency. First one is used for the adjacency data. Second one is used for the rewrite data. And then inside the adjacencies, we are storing data which is needed for specific types of adjacency. For example, if you go down to for indirect adjacency here, inside the adjacency we are storing information what is the next hop. So basically the indirect adjacency allows us to do a second lookup in the FIB. And for the second lookup, this is the place where we are doing the next hop. This is of course if you have unresolved indirect route in the FIB. Another thing which we have here is we are trying to share adjacencies to reduce the load on the cache. So if you have like 1 million routes pointing to the same next hop, we don't want to have 1 million adjacencies in the adjacency table. And the way how we are doing it is very simple. What we are creating basically the signature for every single adjacency. And signature is created by taking the part of the adjacency, part which is between the signature start marker and signature end marker, which is here. We use that part of the adjacency entry. We are creating the hash, and every time when we are trying to create the new adjacency, first we see if that adjacency already exists in the hash. If the result of the hash lookup is positive, then we will not create the new adjacency, but we will install the new route pointing to the same existing adjacency, which is found by the lookup. So with this approach, actually, when you are building a code which is installing the route into the FIB, you don't need to care about if there is the similar adjacency already existing, even maybe which is installed by somebody else. You just need to call the function to install the route, and if it will try to save the space and reuse the existing adjacency if possible. And now the important part here, really the most important part here is this one. IP lookup next index. This is actually the place where you are saying when this adjacency is hit by the lookup, what should be the next node. And here we are using actually what we are defining above in this file, those adjacency types. Next miss, next drop, next local, next ARP, classify, map, rewrite, and so on. So basically, if you want to create your own adjacency type, which will result in the packet going to your graph node, you just need to define the new adjacency type here, and automatically you will start receiving the packets. And that is exactly what we were doing with with map code where we are installing adjacency type map, and packets will just go to the map node instead of going to the rewrite node. At the end of the structure, we have the second cache line. And this is basically data used by the rewrite adjacency. So every time when we install a route, which is going to the rewrite node and which is supposed to leave the VPP on the TX interface, we need to do a rewrite of the layer 2 header. And here we are basically storing the layer 2 header and the size of the rewrite. So IPv4 rewrite node will basically just take the data, it will overwrite the layer 2 header with the data inside the adjacency, and it will send packet out on the interface. A special case which we have, which I would like to mention, is that we are basically supporting the multi-path adjacencies. So you can basically define the equal cost load balancing in FIB, or even unequal cost load balancing in FIB. And that works in the way that basically we are doing per flow hashing, and we are installing the number of adjacencies which basically corresponds to the ratio between the destinations. If you are doing 50-50 load balancing, then it's easy. We are basically installing the two adjacency into the adjacency table, which are linked together, and then we are doing per flow hashing to basically send half of the traffic to the first one, half of the traffic to the second one. If you have some non-equal distribution between the paths, then we are trying to come up with the, I don't know, if you have like 40% going to the left and 60% going to the right, that will result in 5 adjacencies, where each adjacency is representing basically a 20% of traffic. And then 2 of them will go left and 3 of them will go right. And again, we are doing flow hashing to basically distribute the traffic between those 5 adjacencies. And if you take a look into the code, there is some functions which are dealing with multipath adjacencies. It's a bit of black magic, which was written a long time ago. I'm not very familiar with that stuff, but if somebody wants to play with it.
When you add your own adjacency, the index is the index into the next node's table for the lookup node. As a question, is it the index into that list?
It's basically the next. We have a group of graph nodes which are dealing with which are doing lookup. We have IPv4 lookup, IPv6 lookup. We have some other nodes which are also doing the FIB lookups like multicast and so on. So basically, what we are doing, we are maintaining the same group of the next nodes, which is shared between the multiple graph nodes. So
okay, so if I create my own node that I want to
so we are basically have this macro. You see it here, IP4 lookup next nodes. If you want to do the new type of FIB entry next node, you need to add it here. So last one, IPv4 indirect. You can say next one is your something node. You need to define this this value, which is basically this enum field in this. So you basically add the new next node, just look up next node here. So we have the indirect next node, blah blah. You add new one here. Then you add mapping between this next node index and the string into this macro definition. And we have one for IPv4 and one for IPv6. If you take a look, you will see that actually it's always the same name, except in case of ARP. For ARP, we have neighbor discovery.
Okay.
Yeah.
And can you do this from a plugin? So without having
no,
to...
This is something what you cannot do from the plugin. It is doable. I mean, somebody needs to spend a bit of time to really make this doable from the plugin. I don't see any problem to do it. It takes some time to basically reorganize stuff, because if you take a look,
there are actually some nodes that do this dynamically. It's not from a plugin.
Yes. Yes. But then this is a, I mean, it can easily happen that it goes out at some point. So what we really need to do here is to do the proper API to really register node instead of maintaining this list dynamically.
Okay.
Yeah. And if you take a look where this macro is used, you can actually see that there is a lot of files which are using this macro. For example, classify node, which is because all those nodes are doing kind of fib lookups, or they are supposed to send to the. So basically, this macro is about sharing the same set of next nodes which map to the adjacency table.